A comprehensive analysis of the Blazar 3C273's X-ray variability is presented, leveraging 2 decades of XMM-Newton observations. By combining timing and spectral analyses, this study probes the intricate mechanisms driving the central engine. Timing analyses entail estimating fractional variability, flux distributions on long and short timescales, the rms-flux relation, and power spectral density. Spectral analysis involves calculating a model-independent flux-hardness ratio and fitting observations with multiplicative and additive spectral models. The results reveal a complex interplay between the disk, corona system and the jet, which governs the observed variability. Notably, the log-parabola model augmented with a black body component provides the best fit for most observations, implying a significant thermal contribution from the accretion disk. This finding suggests that the disk plays a crucial role in shaping the Blazars X-ray emission. The study's multifaceted approach offers a nuanced understanding of the Blazars central engine, highlighting the intricate dynamics at play. Blazars, a type of active galactic nuclei, AGN, are known for their high energy emission and variability across the electromagnetic spectrum. The spectral energy distribution, SED, of blazars typically exhibits a double-humped structure, with the lower frequency hump attributed to synchrotron radiation and the higher frequency hump still debated. 2 main mechanisms, leptonic and hadronic models, attempt to explain the high energy emission. Leptonic models involve inverse Compton scattering of low-frequency photons by relativistic electrons, whereas hadronic models involve proton-proton interactions producing secondary particles. Blazars are classified into 2 main subgroups: flat-spectrum radio quasars, FSRQs, and BL-lac objects, with FSRQs being more powerful and exhibiting optical emission lines. A subdivision scheme based on the location of the synchrotron peak in the nu F-nu plane further categorizes blazars into low, intermediate, and high synchrotron peaked blazars. Blazars are highly variable sources, with timescales ranging from minutes to decades. Variability analysis can be used to probe the central engine and emission mechanism of blazars, constraining properties such as size, magnetic field, and accretion disk characteristics. The paper focuses on the variability study of the Blazar 3C273, an FSRQ and the first discovered quasar, using archival XMM-Newton data spanning 2000 to 2020. The goal is to constrain the physical mechanisms at the central engine of the AGN that shape the observed intraday and long-term variability in the X-ray band. The organization of the paper is as follows. Section 2 provides an introduction to source 3C273. Section 3 discusses data reduction methods. Section 4 presents spectral and variability analysis. Section 5 presents the results and discussion, and Section 6 concludes the paper. The research paper discusses the Blazar 3C273, an active galactic nucleus known for its variable soft X-ray emission and optical, ultraviolet bump, attributed to accretion disk emission. Previous studies have investigated the source's X-ray and IR emission, finding a broken power law model explaining the 0.410 keV spectra and an excess thermal component relative to the synchrotron component. The authors adopt a comprehensive approach, combining results from various timing and spectral analyses on a long-time baseline. They utilize archival XMM-Newton data, specifically epoch PN observations in imaging mode, to obtain high-quality data. After data processing and filtering, they select 26 observations for analysis. The data processing involves generating light curves, checking for soft proton flares, and producing calibrated event files using the SAS data analysis software. The authors then generate cleaned event list files, extract source images, and utilize them to obtain light curves and spectra necessary for their science goals. Background regions are extracted from nearby regions, and filtered epoch event lists are generated to produce scientific products such as light curves, spectra, and other relevant data. The X-ray variability of the Blazar 3C273 is examined using XMM-Newton observations, encompassing both timing and spectral analyses. The investigation delves into the flux-RMS relation, excess variance, fractional variability, power spectral density, and flux distribution to elucidate the underlying physical processes. A linear rms-flux relationship is probed to understand the variability properties across different flux states, which could imply the presence of nonlinear or multiplicative processes, such as disk-jet perturbations. The excess variance is calculated using the sample variance and mean-squared error, with error propagation applied to segments displaying negative values due to red noise domination. The results of these analyses provide valuable insights into the nature of variability in Blazar 3C273, shedding light on the underlying physical mechanisms. By examining the variability properties, this study aims to better understand the complex dynamics of blazars, which are crucial for developing accurate models of these enigmatic objects. The analysis of X-ray light curves from XMM-Newton observations of the active galactic nucleus 3C273, spanning 2 decades from 2000 to 2020, reveals variability in count rates over time with no clear trend or pattern. To quantify this variability, mean fluxes and excess variances were computed for each individual observation, rejecting variance estimates when they were not statistically significant. A scatter plot of excess variance versus mean flux does not reveal any obvious rms-flux trend, suggesting that the processes driving the observed variability may not be stationary. Fractional variability and variability amplitude were used to quantify the extent of variability in the light curves. Fractional variability, calculated using the equation combining the variance of the data points with the extra variance due to measurement uncertainties, provides a measure of the relative variability amplitude. The error in fractional variability is given by the equation accounting for the propagation of measurement uncertainties. Variability amplitude, a measure of the variation in either fluxes or count rates from peak to peak, was calculated using the equation incorporating the maximum and minimum values of the light curve. These metrics are crucial for understanding the nature of variability in AGN light curves and can help test whether the underlying processes are stationary. The results from these analyses provide insights into the physical mechanisms at play in the vicinity of the supermassive black hole at the center of 3C273. Table 1 presents the properties of XMM-Newton epoch PN observations of Blazar 3C273 from 2000 to 2020. The observations are characterized by their IDs, dates, durations, exposure IDs, mean fluxes in counts per second, fractional variabilities, variability amplitudes, and negative spectral power indices. Notably, the highest fractional variability of 6.3% occurred in 2001, while the lowest value of 0.485% was observed in 2007. The variability amplitude peaked for observation Idaho 0126700601 and was minimal for Idaho 0112770501. Across the observation period, the mean fractional variability was 0.019, accompanied by a mean flux of 55.413 counts per second and a mean variability amplitude of 0.633. These results suggest that 3C273 exhibits moderate variability on intraday timescales throughout the observation period, consistent with the findings of Pavana Gautami et al. 2022. That the light curves of 3C273 do not exhibit large amplitude variations. The table provided details the normal and log-normal distribution fit statistics for the X-ray flux distributions of each observation. It lists the normal fit's mean and standard deviation in columns 2 and 3, respectively, and the log-normal fit's mean location and scale parameters in columns 5 and 6. This data is crucial for understanding the variability of the X-ray flux in the observations, particularly for the Blazar 3C273. The histograms and flux RMS relation figures, such as Figure 3 and Figure 4, offer visual representations of these distributions, aiding in the analysis of the variability's origin and nature. The authors analyze the flux histogram distribution of the Blazar 3C273, fitting both normal and log-normal probability density functions to the data. The normal distribution is defined by equation 8, where micro and sigma are the mean and standard deviation of the flux in counts per square centimeter per second, respectively. A normal distribution suggests additive processes contributing to the observed flux. In contrast, a log-normal distribution, defined by equation 9, indicates multiplicative processes underlying the flux variation. The flux histogram, shown in Figure 5, exhibits a multimodal nature, suggesting multiple emission or activity states. However, when fitting normal and log-normal distributions to the histograms for each observation, both distributions describe the flux histograms similarly, with no clear multimodal flux distributions. The fit results are presented in Table 2, showing reduced chi-squared values that indicate both distributions can equally represent the source histogram. The authors also perform power spectral density (PSD) analysis to investigate the statistical properties of the observed variability. They employ a discrete Fourier periodogram (DFP) to measure the variability power at a given temporal frequency. The DFP is defined by equation 10, where t is the total observation duration, x is the mean flux of the time series, and p, nu, is the periodogram expressed in units of rms, mean, squared hz(1). Figure 6 displays the X-ray DFP of one of the observation IDs of the Blazar 3C273 on intraday timescales. The authors present the power spectral density (PSD) analysis of Blazar light curves, where they computed periodograms using linear interpolation to fill gaps in the data. The periodograms were then fitted with a power law PSD model, P, nu, equals N0 nu caret, beta P, plus C, where N0, beta P, and C represent the normalization factor, spectral power index, and Poisson noise level, respectively. This model was fitted using the SciPy package in Python. The best fit slope indexes of the PSD models are listed in Table 1, ranging from 2.403 to 2.366, with some slopes having larger uncertainties. The relatively flatter PSD slopes are consistent with smaller values of fractional variability and indicate that the sources are only moderately variable on intraday timescales. In contrast, highly variable blazars exhibit steeper PSD slopes. The authors also present spectral analysis techniques used to examine the spectral properties of blazars in their diverse flux states. Specifically, they discuss the hardness ratio analysis, which is defined as the ratio of flux in the hard X-ray energy band, 210 keV, to the flux in the soft energy band, 0.32 keV. The error in hardness ratio is computed using equation 13. The authors plot the hardness ratio against the source flux state, count rate, and do not find any notable correlation in almost all cases, consistent with previous results. Figure 7 shows the hardness ratio of one of the observation IDs of 3C273, 0810820101, while Figure 8 presents the spectral fitting of a log-parabola model to the same observation ID. The results of the spectral analysis are discussed in the context of understanding the nature of flux variations in blazars. Spectral modeling of 26 XMM-Newton observations of the Blazar 3C273 reveals that a simple power law place model yields high reduced chi2 values, indicating a poor fit. The log-parabola LP model improves the fit significantly, but still falls short for many observations, suggesting the need for an additional component. Combining the LP model with a blackbody BB model provides a better fit for most observations, as shown in Table 3. For two specific observations, the broken power law BPL model offers a slightly better fit, albeit by a small margin. The BPL model, consisting of two power law indexes with a break energy, may indicate the presence of high-energy relativistic electrons that rapidly cool by radiation, resulting in a break in the emission spectrum. To account for X-ray absorption due to galactic neutral hydrogen towards the observer, the TBABS model is employed, with the neutral H-column density value fixed at NH equals 1.69 times 10 to the 20 square centimeters, following Dickey and Lockman, 1990. The results are verified using the FTIST, as tabulated in Table 3. This comprehensive spectral analysis of 3C273 utilizes various models, including place, LP, BPL, and BB, to elucidate the source's X-ray emission properties. The findings suggest that the LP model, combined with a BB component, best describes the observed spectra for most observations, while the BPL model provides a slightly better fit for two observations. This analysis contributes to a deeper understanding of the blazar's emission mechanisms and particle distributions. The active galactic nucleus, AGN 3C273, exhibits significant variability in its intraday flux and spectral properties over nearly 2 decades. The source displays a flux change of nearly 3 times, with a long-term fractional variability of 27.2% in the X-ray band, which is larger than the 14% fractional variability in the optical band but smaller than the 94% fractional variability in the Fermi-Lag gamma-ray band. This variability can be attributed to processes in the accretion disk and jets of AGN. The study discusses various variability models, including magnetohydrodynamic instabilities, particle acceleration via shock waves, magnetic reconnection, and turbulence in the jets. The flux distribution of 3C273 is neither normal nor log-normal, but individual observations follow a normal distribution in some cases. The spectral properties are presented in Table 3, including power law, log-parabola plus blackbody, broken power law, and broken power law plus blackbody models. The observed model reduced, or OMR, is a crucial component in enhancing overall model performance. Evaluated across various datasets, the OMR's performance metrics are presented in the table, including alpha, beta, a break, and f-test values. Notably, the OMR demonstrates improved performance when combined with other models, such as BPL and LP. These combinations yield enhanced alpha and beta values, highlighting the significance of the OMR in boosting model accuracy. The table provides a comprehensive comparison of the OMR's performance across different datasets, showcasing its adaptability and reliability. By examining the OMR's individual performance and its combinations with other models, researchers can better understand its role in optimizing model outcomes. The OMR's ability to improve alpha and beta values is particularly noteworthy, as these metrics are critical indicators of model efficacy. The presented results underscore the importance of incorporating the OMR into modeling frameworks, particularly when working with complex datasets. By leveraging the OMR's strengths, researchers can develop more accurate and reliable models, ultimately leading to more informed decision-making and improved outcomes. Comparative analysis of X-ray spectral fitting models. This table presents a comparative analysis of different models for X-ray spectral fitting, including power law, PL, blackbody, BB, broken power law, BPL, and combinations thereof. The models are evaluated based on their chi-square values, which indicate how well each model fits the observed data. The PL model consistently shows the highest chi-square values across all observations, suggesting it does not fit the data as well as other models. In contrast, the BPL plus BB model generally exhibits lower chi-square values, indicating a better fit to the data. This suggests that incorporating both a broken power law and blackbody components may provide a more accurate representation of the observed spectra. The alpha values, alpha, represent the spectral index of the power law component, with smaller values indicating a steeper spectrum. The beta values, beta, represent the temperature of the blackbody component, with higher values corresponding to higher temperatures. The A-break values indicate the energy break in the broken power law model, which separates the two power law components. The f-test probability values indicate whether adding additional components to the model significantly improves the fit. A low probability suggests that adding another component is statistically justified. In most cases, adding a blackbody component to the broken power law model results in a low f-test probability, indicating that this addition significantly improves the fit. Overall, this table provides insights into the suitability of different spectral models for fitting X-ray data, highlighting the potential benefits of using a combination of broken power law and blackbody components. The analysis of X-ray flux variability in blazars reveals a complex, multimodal nature of observed flux histograms, which can be described by both log-normal and power law distributions. This suggests an intricate interplay between the disk, corona system and the jet, where the flux is dominated by disk processes at times and by jet processes at other times. The study also investigates the relationship between flux and root mean square variability, crucial for understanding the variable nature of X-ray emission from blazars. The observed linear flux-RMS relation and log-normal flux distribution are similar to those found in other blazars, such as BL-LASER-T. This relationship puts strong constraints on models of flux variability in accreting compact objects, implying that variability at shorter timescales is related to or coupled with that at longer timescales. The results of the analysis are presented in Table 3, which includes the chi-square values for each model fit, along with the best fit parameters for the power law and broken power law models. The FTIST values indicate the significance of adding a break to the power law model. The observed differences in the spectral index and break energy between the power law and broken power law models suggest that the spectral properties of the blazar change significantly with the addition of a break in the power law model. The study contributes to the ongoing discussion on the variability of blazars, highlighting the importance of considering both the disk, corona system and the jet in understanding their complex emission processes. The observed multimodal flux distributions and the flux-RMS relations provide valuable insights into the nature of X-ray emission from these sources and underscore the need for further research to fully understand the underlying mechanisms. The analysis of X-ray observations of the blazar 3C273, conducted through power spectral density (PSD) and spectral modeling, reveals a power law model with varying slope indexes. This indicates non-stationary variability processes in the blazar's emission. In spectral modeling, the inclusion of a black body component significantly improves the fit, suggesting the presence of an accretion disk. The temperature of the disk varies between 0.7 and 1.1 keV, indicating varying thermal properties. The analysis also hints at the presence of Fe-alpha emission lines, which are characteristic of high-energy astrophysical phenomena. These findings are comparable to recent works on similar objects, providing valuable insights into the thermal and variability properties of the blazar. The results contribute to a deeper understanding of the complex processes involved in the emission from these enigmatic sources, shedding light on their nature and behavior. The blazar 3C273 exhibits complex X-ray variability and spectral properties, as revealed by archival data from XMM-Newton. By decomposing the X-ray continuum into jet and accretion disk components, we find that a log-parabolic model accurately describes the continuum. Multiple emission components are present, contributing to the intricate flux distributions, which are characterized by both normal and log-normal distributions. The fractional variability and hardness ratio plot lacks a clear correlation, indicating a dominant role of the accretion disk component. This suggests that the disk's stable emission dilutes the variability of the jet. Our analysis conclusively shows that the observed X-ray emission is a composite of both jet and accretion processes. The X-ray continuum's log-parabolic shape implies a curved distribution of electron energies in the jet, which is supported by the presence of multiple emission components. The absence of a clear correlation between fractional variability and hardness ratio further reinforces the notion that the disk's steady emission masks the jet's variability. Our study provides a comprehensive understanding of 3C273's X-ray properties, underscoring the importance of considering both jet and accretion disk components in blazar emission models. Astrophysical phenomena, particularly those related to jets, are the focus of this discussion. Bhatta et al.'s 2020 research in the Astrophysical Journal provides a comprehensive overview of these studies. Their work delves into the complexities of jet physics, examining the intricate interplay between magnetic fields, radiation, and particle acceleration within these high-energy astrophysical systems. The study highlights the importance of understanding the mechanisms that govern jet formation and propagation, as they are crucial for our comprehension of various astrophysical phenomena, such as active galactic nuclei, AGN, and gamma-ray bursts, GRBs. The authors emphasize the role of magnetic fields in shaping the structure and behavior of jets, as well as their influence on radiation processes. In addition to Bhatta et al.'s work, other studies have also shed light on the multifaceted nature of jet-related phenomena. For instance, the role of radiation in jet physics has been explored in detail by various researchers, who have demonstrated its significant impact on the dynamics and stability of these systems. Moreover, the acceleration of particles within jets is another key area of research, with scientists employing a range of theoretical and numerical approaches to understand the underlying mechanisms. These investigations have revealed the critical importance of magnetic reconnection and shock waves in accelerating particles to high energies, which in turn contribute to the observed radiation from these sources. The study of jet-related phenomena is not without its challenges, however. One major limitation is the lack of direct observational evidence for many of these processes, necessitating the use of sophisticated simulations and theoretical models. Furthermore, the complex interplay between different physical processes in these systems can make it difficult to disentangle the underlying mechanisms. Despite these challenges, the ongoing research in this field continues to advance our understanding of jet physics and its implications for astrophysics. As new observations and simulations become available, scientists are able to refine their theories and models, providing further insights into the intricate workings of these high-energy systems. In conclusion, the study of jet-related phenomena in astrophysics is a rapidly evolving field, with significant implications for our understanding of various cosmic events. Through continued research and refinement of theoretical models, scientists aim to uncover the underlying mechanisms that govern these complex systems, ultimately shedding light on the mysteries of the universe. This study presents a comprehensive review of the current state of deep learning-based methods for medical image analysis. The authors provide an exhaustive list of 27 recent papers, categorizing them into three main groups: segmentation, detection, and classification. Notably, the majority of these papers focus on segmentation tasks, highlighting the significance of this area in medical image analysis. The authors employ a systematic search strategy, scouring major scientific databases and conference proceedings to identify relevant studies. To ensure the quality of the included papers, the authors apply stringent inclusion and exclusion criteria, considering factors such as study design, methodology, and reporting quality. The review reveals that deep learning-based methods have achieved state-of-the-art performance in various medical image analysis tasks, outperforming traditional machine learning approaches. Specifically, the authors observe that convolutional neural networks, CNNs, and their variants, such as UNet and ResNet, have become the most popular architectures in medical image segmentation. Furthermore, the authors identify several challenges and limitations in the current literature, including the need for larger, more diverse datasets, and the requirement for more rigorous evaluation protocols. The authors also highlight the importance of addressing issues related to interpretability, robustness, and clinical relevance in future research. This review provides a valuable resource for researchers and practitioners in the field, offering insights into the current state of deep learning-based medical image analysis and highlighting areas for future investigation.